Hi everyone, I'm Hsien-chin. I'm a PhD student from the Dialogue System and Machine Learning Group in Heinrich-Heine University. Today, I would like to talk about the domain-independent user simulation with transformers for task-oriented dialogue systems. How to find a proper environment when you want to train a dialogue system by reinforcement learning. Training systems with real users is time-consuming, and optimizing systems with noisy feedback from real users is unstable. How about training from a corpus? The dataset is not interactive and only includes a limited amount of trajectories. In other words, by training with real users or using datasets, the system is not able to explore all possible paths because of the limited coverage. Therefore, training with user simulators, a more efficient, controllable, and interactive environment is widely used in research, especially rule-based user simulators. However, you may find out their behavior is quite different to real users. In addition, you need to rewrite the rules carefully when you want to expand your model to a new domain. Rewriting the rules takes lots of time, and designing rules for complex scenarios is very challenging. On the other hand, the statistical user simulators can learn the user policy from datasets, but they are still domain dependent, which means you need new labels, you need to modify the feature representation, or you need to retrain the whole model by moving these models to new domains. We view user simulation in a task-oriented dialogue as a sequence-to-sequence problem, which means the user's model predicts the value of each slot in the input sequence. In addition, the model should be domain independent so that it can generalize to new domains easily without modifying or retraining. Thus, we proposed a transformer-based user simulator, TUS. Let's take a look at its structure and feature representation. With its transformer structure, this model can deal with various length input sequences and capture contextual information. The input sequence is composed of slots from the user goal and inputs and slots mentioned by the system. The order of the slots takes into account the user's priorities. A slot placed before another one means it is more important. The previous turns are also presented in the input. The whole sequence starts with a spatial token series, and there are separate tokens between each turn sequence. The input feature of each slot is represented by statistical features. For example, whether the constraint slot is fulfilled and which type the slot belongs to, a constraint or a request. In some cases, multiple slots may share the same statistical feature, and it makes the model difficult to distinguish one slot from another. Therefore, we give each slot a dialog scope identity. This identity is generated randomly, and the slot has it just for the duration of one dialog, which means it can be changed in other dialogues. In this way, the model can still distinguish between slots even if their other features are similar. The output target is also domain independent. Instead of predicting which value belongs to the slot, the model predicts where the value comes from. For example, copying the value from the user goal or the system state. The target of the first token is about which domain should be mentioned. Instead of selecting certain domains from the ontology, the model predicts which domains in the user goal should be mentioned. By this setting, TOS can mention 6 different domains in one dialog at most. The maximum number of domains is predefined, so it can be more than 6 if you want. Because the domain is domain independent, you don't need to modify the input representation and output target when adapting to new domains, adding new slots or new values to the ontology. In other words, TOS can transfer to new domains without redesigning the future representation or retraining the whole model. We trained our model on the multi-worlds 2.1 dataset, consisting of dialogues between two humans, one posing as a user and the other as an operator. There may be more than one domain involved in one dialogue, even in the same turn. During training and testing with the dataset, we ordered the slots in the inputs list based on the data, which means a slot is before another if it is mentioned earlier. For inference without the dataset, such as when using TOS to train a dialog policy, the order of slots is generated randomly. User simulators are designed to train dialog policies. Thus, a better user simulator should result in a better dialog policy, which means we can evaluate the user simulator based on the performance of policies. We train different dialog policies by proximal policy optimization, a simple and stable reinforcement learning algorithm with a rule-based baseline, agenda-based user simulator, a data-driven baseline, variational hierarchical sequence-to-sequence user simulator, and the proposed model, TUS, as user simulators in the CompLab 2 framework. The policies are trained for 200 epochs, each of which consists of 1,000 dialogues. Each dialog policy is trained on 5 random seeds. To test the ability of TUS in handling unseen domains, we removed one domain during supervised learning of TUS. When training dialog policies, the user goal is generated randomly from all possible domains. Some domains in multi-worlds may share the same slots, such as restaurant and hotel domains, which contain property-related slots, like area, name, and price range. However, the corpus also includes domains that are quite different from the rest. For example, the train domain, which contains many time-related slots such as arrival time or departure time, as well as unique slots such as price and duration. We use direct and indirect methods to evaluate our model. With direct methods, we measure how close our model can fit the dataset. With indirect methods, we use cross-model evaluation and thus demonstrate the generalization ability of the policy trained with a particular user simulator when evaluated with a different user simulator. In addition, we implemented a zero-shot transfer experiment to evaluate how well TOS can handle unseen domains by leave one domain out training. We also performed a human evaluation. Policies trained with different user simulators are evaluated in interaction with paid users. The policy trained with TOS performs well when evaluated with the agenda-based user simulator, with a 10% absolute improvement in the success rate over its performance on TOS. On the other hand, while a policy trained with the agenda-based user simulator performs almost perfectly when evaluated with itself, the performance drops significantly by 35 absolute when its policy interacts with TOS. The variational hierarchical sequence-to-sequence user simulator is neither able to train nor to evaluate a multi-domain policy. We suspect that this is due to the fact that this model was designed to operate on a single domain and does not generalize well to the multi-domain scenario. To the best of our knowledge, no other data-driven user simulator has been developed for the multi-domain scenario. Then we evaluated policies trained with different user simulators in interaction with humans. We collected 400 dialogues for each policy. The success rate measures whether the given goal is fulfilled by the system, and the overall rating grades the system's performance from 1-star poor to 5-star means excellent. TOS is able to achieve a comparable success rate as the agenda-based user simulator without domain-specific information, and even scores slightly better in terms of the overall rating. For leave one domain out models, the performance of TOS no attraction is similar to the one of agenda-based user simulator and TOS, without a statistically significant difference. We do, however, observe a statistically significant decrease in the success rate of TOS hotel when compared to TOS in agenda-based user simulator. This is unsurprising, as the hotel domain accounts for around 40% of the training data. For both TOS no attraction and TOS no hotel, the success rate on the domain attraction is comparable to TOS and agenda-based user simulator, but the success rate on the domain hotel is relatively low. In other words, removing a domain does not decrease the success rate in the corresponding domain, as the future representation is domain agnostic. Instead, it impacts domains that need plenty of data to learn. In conclusion, we proposed a domain-independent user simulator with transformers TOS. We designed domain-independent input and output feature representations. Our model outperformed the variational hierarchical sequence-to-sequence user simulator, the state-of-the-art data-driven user simulator. Besides, TOS is comparable with the agenda-based user simulator, a rule-based user simulator, even though it is based on carefully designed domain-dependent rules. In comparison to previous domain-dependent user simulators, TOS can handle unseen domains without feature modification or model retraining, even with fewer training samples based on the result of the zero-shot transfer experiment. In future work, we would like to learn natural language generation to make TOS more human-like and apply reinforcement learning to its model to improve its performance. This work is part of the European Research Council-funded project DIMO. Thank you for listening, and I look forward to your questions.